Hello everybody, my name is Mike Bartles and I'm the current HEC HMS team lead. This video is a recording of our third quarterly HEC HMS webinar which was presented on September 23rd, 2021. Over the past 2 years, the HEC HMS team has leveraged the HEC two-dimensional solver, which was pioneered by the HEC RAS team to add advanced flow and sediment transport modeling capabilities to HEC HMS. These capabilities allow engineers to perform detailed investigations within complex watersheds and riverine systems where other hydrologic methods are not adequate. In this webinar, myself, Dr. Jay Peck, and Nick Van will discuss these new features and provide demonstrations of their usage. As I previously stated, I am the current HEC HMS team lead, and I led the development effort to integrate these 2D features within HEC HMS. Dr. Jay Peck is the surface erosion and debris flow expert on the HEC HMS team and is a master of all things related to sediment transport. Nick Van is a computer scientist who specializes in software compilation and deployment features and has been instrumental in getting HEC HMS and its myriad of dependencies compiled and ready for use by macOS and Linux operating systems. So without further ado, we'll get started. Hopefully everybody enjoys this picture. Unfortunately, this area was recently subjected to some forest fires. This is right outside of Lake Tahoe and Upper Truckee River watershed, but I'm sure it'll be back as strong as ever in the future. So within this presentation, we're going to discuss first and foremost why we added the 2D flow and sediment transport capabilities to HMS. Go over a little bit of the technical background and significance of these features, talk about what you can do that you couldn't before. We'll demo them within the software, show you how everything looks in the user interface and how you can interact with them. And then we'll finish with tech transfer documentation and discussion of our next steps and plan future improvements, and then take some questions at the very end. So I'm going to present 2D flow first, and then Dr. Pack is going to be presenting 2D sediment afterwards. I'll go first, Jay's going to go second. So we're getting the sediment for sure. After Jay, we're going to switch over to Nick for a quick demo of these features in Mac 2. So this image right here is the Schuylkill River flooding in Conshohocken, Pennsylvania on September 2nd, 2021, in case you were wondering. So a little bit about the objectives first. We set out to implement the 2D solver that was pioneered by the HEC RAS team within HMS as part of a USACE R&D project. So this is going to expose the 2D solver to a new array of hydrologic applications that it hasn't been exposed to before. This is a shared computational engine between the RAS and the HMS teams. As improvements are made to the solver, we both benefit from it. So hydrologic applications usually involved precipitation being applied to the overland plain, infiltration, evapotranspiration, snow melt, base flow, things like that it hasn't necessarily been exposed to before. As we make improvements, RAS benefits. As RAS team makes improvements, the HMS team benefits. This has been an absolutely great collaboration experience between all of us, and development is still ongoing. We also set out to release the 2D flow and sediment transport capabilities to a wider range of platforms, including Windows, macOS, and Linux. So HMS has historically been released for Windows over the past year and a half or so. We've also included macOS and Linux. So Nick Van is going to show a quick demo at the end of using these features in macOS as well. That's the first time that you'll be able to use 2D flow or 2D sediment transport capabilities on either macOS or Linux as well. So this slide highlights some of the major differences between the 2D flow capabilities within HEC RAS and HMS. I'm not going to bore you to death with discussions of how each cell is treated with an elevation volume curve. Each face gets essentially a cross section. You can go into a lot of detail, and there is detail already available for you to look at RAS documentation wise for that. What I want to highlight here are the differences between HMS's implementation and HEC RAS's implementation. In HMS, currently you only have access to the 2D diffusion wave equation set. Cannot use the full momentum equations, but we do have plans of adding that in the future. In the future, we'll allow access to the full array. Right now, you can choose between a fixed and Courant-based time step. So if you're using the Courant-based adaptive time step, that algorithm is ever so slightly different from HEC RAS. Again, we're trying to fine-tune this for hydrologic applications and make it easier to interact with. And off the shelf, able to go for hydrologic applications. When it comes to infiltration, things start to get more different. So we separate our calculations for hydraulically wet and dry portions of each cell. So essentially each cell gets 2 infiltration calculations. And we also, every single infiltration method that's in HMS is available to be used with the 2D flow area. So you can use initial and constant, You can use deficit and constant. You can use green and amped. You can use layered green and amped. You can use soil moisture accounting. You can use all the infiltration algorithms that are available within HMS for 2D modeling exercise. The differences between HEC RAS and HEC HMS continue going from there. So whereas HEC RAS computes a single infiltration rate per cell, so essentially computing the HEDA graph and taking off losses and whatever is left over is excess on the cell, we actually allow water to be dynamically infiltrated, so to say. So say precipitation is really heavy in one portion of the watershed, or infiltration capacity is less over there. Either way, excess is generated in that portion of the modeling domain, in that portion of the 2D area, and it flows downhill. If precipitation is less downhill, or infiltration rates increase as you go downhill, that water that was runoff in the upper part of the watershed can infiltrate downstream. So we allow that to happen. We also allow for the integration of canopy and surface depression storage when using 2D flow, and base flow. Right? So linear reservoir is usually our go-to method for base flow computations, especially when it comes to 2D flow. We actually added a capability where you can actually get water to come back out of the ground. So you can simulate interflow where water is infiltrated and then exfiltrated back out within the same cell, and you can return back to the surface. So those base flow computations are available when using HEC HMS. I want to highlight the validation and verification that we did go through. So you don't just have to trust us with this one. We did go through a lot of effort to make sure that the computations in HMS are producing the correct results when we're using these 2D flow computations. So first and foremost, we use some off-the-shelf published data sets from Hunter and SIA. The Hunter data set is shown there on the left for a number of locations and number of time steps. We verified that the computations are producing the correct water depths and velocities. On the right-hand side is a really cool application where there's like kind of a roundabout plane where you apply precipitation to it and it goes around that outlet and can flow out the bottom there in the center. That's from that SIA data set. We can compare the differences between what HMS is producing and what's been published. Also, we do a lot of effort where we essentially generate the exact same modeling domain in HEC RAS, or generate a model for the exact same modeling domain in RAS and HMS, verify that the two are producing the exact same results. This is what I'm showing here for Redwood Creek. We hold as much as possible as we can, or much constant as we possibly can. So in this case, we'll get rid of infiltration, we'll get rid of base flow, things like that, apply precipitation uniformly over the modeling domain and make sure that we produce the exact same results at the outlet, right? So we want to verify that if you're doing the same thing in HMS as you're doing in HEC RAS, holding everything constant, you're going to get the exact same output here. And that's what we're showing in the slide here. So this is really important to me. What can you achieve that you couldn't before? So this isn't just another bell and whistle that we added on here that we're expecting everybody to use every single time they go out here and build a model. HMS is a unique tool within the H&H Communities toolbox, and that you're not forced into using the processes or a single process or whatever that we're saying when you choose HMS. You have an array of infiltration methods that you can use, an array of base flow choices that you can use. You can use gridded or lump precipitation. You can or cannot, turn on evapotranspiration, things like that. You're not forced into using stuff. It's up to you to choose what is pertinent for your modeling application in both space and time. So not every single situation warrants the most complex solutions, right? In a lot of cases, hydrologic routing routines are more than adequate. They're also faster, right? Also, if you want to use these complex routines, you shouldn't be required to change the entire modeling domain. Just change what you want, where you want it to simulate the complex stuff, right? So almost all aspects of HMS needed to be modified to effectively utilize these 2D flow and sediment transport capabilities. So that includes the UI, because we need to allow you to have access to parameterize these things. The model code that communicates between the UI and the compute code, the way in which we plot and tabulate stuff, and the way in which we show results in space. So spatial results were a big one. All of this stuff is still ongoing, but all of these things needed modifications for sure. So I want to show a really quick example where these capabilities are essentially needed. You can't really do a good job without them. So a great example is here. The Truckee River is flowing through Reno and Sparks, Nevada. So the Truckee River, as you can see, flowing from the top of the page, comes from a really, really incised channel, a lot of mountains on either side of it, not a lot of space for water flow either way. In the overbank, then you get to Reno and Sparks, and water can go everywhere. all left and right. It can stop, go backwards. There's all sorts of crazy stuff that can happen through here. This has happened periodically as the channel capacities have been exceeded and caused significant damage. Most recently, the 1997 flood event in January affected the city and the international airport. So there aren't too many examples that I've seen out there where you got water standing on the runway, almost up to the engine nacelles and on an international airport. But that happened here. Channel capacities were exceeded, water went all over the place. You had water spreading out laterally. So as part of a SWIMS implementation in Truckee River, an HMS model was built and used unihydrograph transform and hydrologic routing through this area. The Truckee River, like I said, upstream is super incised, and those methods work fine to compute runoff rates upstream of Reno, but the slope drastically decreases as you go through Reno Sparks. Hydrologic routing methods don't work too well when channel slopes decrease, especially below about 2 feet per mile. They all start to break down a bit, and water gets out of bank and spreads laterally. Hydrologic routing methods don't do that as well. As you can see, results downstream, not so good using hydrologic routing. Blue is computed flow, black is observed flow in this case, drastically overestimating or underestimating attenuation and translation because we're not simulating water going on the overbank using hydrologic routing methods. So what I did was I took this model and I merged those 3 subbasins that you see there in the middle into a single subbasin, replaced that with a 2D area, replaced unihydrograph theory with a 2D area, and all the hydrologic routing methods for the channels with the 2D area, and allowed water to flow where it was going to flow in the overbanks and all the other places. And you get much, much better approximations of translation and attenuation processes here. So I'm allowing water to flow in the overbank. It can stop, it can flow backwards, and it can move on downstream then when it's ready, because there's a pretty good constriction as it goes past that gauge, that Vista gauge through here. So again, highlighting, this is a very, very good application. You cannot do this with hydrologic routing. 2D flow is essentially the only way that you can do this. We'll take a closer look at some of these results later on here. All right, so I want to demo a little bit how you go about doing some of this stuff. First, I'm going to show a very simple example. I'm going to start with a watershed that's outside of San Francisco called Redwood Creek. So if you've ever been to Muir Beach, Redwood Creek flows in to the Pacific Ocean right there at Muir Beach. Beautiful, beautiful area. I first and foremost built this model using unihydrograph theory. Straightforward application, only a few grid cells. I think the modeling domain is about 7 square miles in size. Unihydrograph theory does great, but now I want to actually use 2D flow just for a demonstration. So what I'm going to do is I'm going to create a brand new basin model. I'm going to call this one 2D. So Redwood Creek 2D. So everything is the same before what I had. It's all the same within this new one, but now I want to replace unihydrograph theory. So the Mod-Clark unihydrograph transform that I have in here already with 2D flow. I have a mesh ready to go. Things that I want to highlight as part of this. Got to use a mesh that's generated by HEC RAS right now. In the future, we will allow you to generate the meshes in HMS, but RAS Mapper is really, really good at generating a mesh. You can do a lot of really cool diagnostic tools. You can add break lines. You can do refinement regions, all that stuff right there. So if you're handy at building meshes in RAS, keep doing that. Right? You can import a mesh ready to go, just like that. So what I'm going to do is I'm going to go to File, and then Import, and then HEC RAS HDF file. And now you got to choose where this mesh actually lives. So what I like to do, here I'm going to show you this quick. I have my project directory where all my HMS project files are stored. Keep that in here. The data directory is where we expect you to put all this data. So all of your observed time series, precipitation, so on and so forth, keep that in here. Keep it going too. It's your HDF file in here that contains the RAS, or that contains the mesh that you generated within HEC RAS. I'm going to copy that location. Paste that in here. I'll select that one. And now I got to select the basin model that I want to actually use. So I have 2, right? I just created that copy. I'm going to go to 2D. Now I want to select the subbasin that I want to actually apply this mesh to, right? Only georeference subbasins are allowed to be used. You can't just make stuff out of thin air here. So we're requiring you to georeference your elements in order to use 2D flow within HMS. That's the way that everything is going anyways, so I don't think that'll be too much of a limitation for anybody in here. But I have a single subbasin. That choice is easy. If you had many subbasins, this list would be populated with many subbasins, but I only got one right now. So let me select that one. And now within that selected HDF file, I have one single mesh. If I had many meshes, I would be able to choose in here. You can only select one right now, so this is easy. I only got one. It's got approximately 3,100 cells, and there's one boundary condition line for that. So I'll go ahead and click Finish, and now that'll be imported here. And notice that I changed my discretization from a Mod Clark, a typical 2 kilometer by 2 kilometer grid cell that I had from before. Now I'm using unstructured mesh, so the cells can have up to 8 sides. All can be irregular. We're not forcing it to be on Cartesian coordinates or anything like that. Everything that you can do in RAS, every kind of mesh that you can use in RAS, you can use in here as well. So now we got that mesh in place. And I want to show you the differences between the component editors that you looked at before. So if you're used to looking at the component editor like this, we start with the discretization on top, then canopy, then surface, then loss, then transform, then base flow. Still the same setup here with 2D flow, except now we've replaced the structured discretization that I had from before with the unstructured folder. And within that folder, we contain things that are pertinent to the mesh, right? The boundary conditions, or essentially the way in which water can leave or enter that 2D area, is a part of the mesh. So if I go and click on that, this is the 2D connections associated with that. It's actually located right down here. Let me turn that off so I can show you. You can see that red line right there. That's the 2D connection. That's the way that water can actually leave this area. It is a normal depth boundary condition. So it's already specified as a normal depth, but you can specify it as up to 4 different types. So you can have a stage hydrograph, flow hydrograph, rating curve, normal depth, so on and so forth. But that's normal depth. I'll set the ratio of subbasin flow to 1. What that implies is that all base flow is generated within the subbasin goes to this connection. That's where this is going to come out. You can have bifurcations, right? So I can have like 4 different ways that water could leave or enter, whatever, this modeling domain. Base flow is a mathematical transform. It's no dimensional, kind of like unihydrograph theory. So you need to specify where it's going to go. So I'm saying every single ounce of base flow that's generated goes here. If I had 2 boundary condition lines, maybe I would say 50% goes to one and 50% goes to the other, or 20/80, or 10/90, whatever. But I only have one, so I'm going to go with that one. And I'm also going to connect it to Mere Beach on the downstream side. One other modification that I got to make, so I'm going to make a modification to my meteorologic model to allow the subbasin in here. Include that. Oh, before I go any further too, the controls for the actual 2D computations are contained within the 2D diffusion wave component editor. So similar to Mod Clark, now you have a transform, this 2D diffusion wave. You should be used to these computations if you've seen them before in RAS, something like the implicit weighting factors, theta, the inner and outer tolerances, the solution scheme, the number of iterations that were allowed within here. Like I talked about before, the default time step is going to be adaptive. This is pertinent or applicable to most hydrologic applications, but you do have the option of using a fixed time step where you just say use 10 seconds everywhere and all time. This allows it to change based upon the Courant condition or the Courant number within the modeling domain. You can specify a warm-up period if you want. And you can also say this is how many cores I want you to use to actually compute flow and sediment transport within this mesh here. So this goes all the way up to the number of cores that you have on your machine. I have 8, they're hyper-threaded, so I get 16 choices in here, all the way down to 1. More cores is not always better too. I'm sure you guys are aware of that, but I think 4 is a pretty good approximation of most setups. And then I would create another simulation. I'll call this April 2018 2D. Select the basin model, select the MET model, select the control specifications, and I'm ready to rock and roll. I can kick that off and it can compute. While that's computing, let's jump over here to look at the Truckee River example. So I'm going to show you guys some more complicated things that can come about from when you actually go about simulating these things and results that are available for use. So like I said before, you don't have to change anything, right? Upstream of where you want complex things to be going on. Notice that I'm still using unihydrograph theory in your normal 2 kilometer by 2 kilometer grid cells upstream to convert runoff into outflow at the subbasin outlet. But where I wanted definition, I can have it here. Notice that I've also included break lines, right? So like I said before, RasMapper does meshes really, really, really well. You can use break lines, you can use refinement regions and all sorts of really cool stuff in there. Keep using that and just import the mesh into HMS. So in this case, I have 4 2D connections, 3 in, 2 or 1 out. One is right here, one is right there, one is right there. Let me actually turn this on. 2D connections. So you can see where those are located. And you can see where they're all hooked up, so on and so forth. When you compute the simulation, you get new results on the time series tab, or new time series results on the results tab. So I'll go ahead and show you those ones. Within the subbasin here, now I'm going to have a 2D connections folder that contains the results for all of the 2D connections. So in this case, again, I have 4. They all contain time series. 3 of those are inflow, so you can look at all the different inflows that come in. Here is the outflow. So there's surface flow, there's base flow that's generated there, there's total outflow, there's cumulative outflow, and there's stage that's computed for every single one in this case. So look at all those different time series that are available there. Jay will show you even more in the future as well. Last thing I promise, usually this is what people like to see the most. You can also look at additional spatial results, right? So if you have spatial results turned on, you get new spatial results available for 2D areas. So specifically, we're going to talk about hydraulic depth. So what does water look like on the overland plane? So you can animate that go through. Look at water surface elevation, and you can also look at cell velocity. So let me turn on cell velocity too. Really cool thing about this modeling domain is you can start to see, like, over time, okay, everything is confined to the channel. It's flowing pretty quick through there. As I start to get more and more water, it spreads out in the overland plane. And you also get flow coming down rills and whatnot, and in the upper portions of that subbasin. But you get water stacking up here, and velocities fall down and essentially stop, right? So as it flows out in the overland plane, they stop there. Also, I want you guys to notice that we've added tooltips to show you what the specific results are for the cell in which you're hovering right now for that time step, right? So I have cell velocity selected. I have this specific time step 0800 January 2nd, 1997. I can see what that specific value is. And I can also right click and plot spatial results, and you can see a time series of the value that's contained within here. So these capabilities aren't just for 2D flow spatial results. Again, I can look at SWE. If I wanted to, I'll plot SWE throughout here, so you can see SWE melts away here. I'll hover over another cell. There's 0 SWE at that point in time, but I can plot it, and it went from 2 down to 0 and then accumulated a bit over here like this. So spatial results have been buffed recently. Very cool stuff. Let me check here real quick. Yeah, that's pretty much all I wanted to show here. I really want to leave enough time for Jay to go about and showing his cool stuff. So Jay, let me kick it over to you.
Okay, let me share my screen here. Okay, so now I want to change my gear from the flow to the sediment. It's like offload. I think you guys more fun with this offload driving. Okay, so next slide here. This is kind of a background in terms of 2D sediment transport feature in HEC HMS. We are exactly same sediment engine like HEC RAS, but we need something kind of simplification because to reduce some computational complexity or some kind of a memory issue. Okay, first one is non-equilibrium total load transport we're using, but we eliminate diffusion term. We just using advection term. Okay, and then also we're using kind of mixed cohesive and non-cohesive, sediment transport. As cohesive for kind of clay and silt, we're using clone and partner method. For non-cohesive part is we're using sand and gravel. That portion we're using hydraulic erosion and deposition equation. Okay, so it's like HEC RAS, we're using this kind of subgrid, the bathymetry. Using this subgraded, we have wet area and the dry area. Based on that dry portion, we're using sheet and spread erosion equation for erosion, but there is no deposition inside the dry area. The wet area, we're using hydraulic erosion and deposition equation. Okay, but we have some assumption. We just using fixed bed elevation. We not updated this bed elevation based on the deposition and erosion information. Okay. Also, one assumption in here, we just using one layer and the one gradation per cell. Now, HEC RAS, we're using kind of different value even inside the cell. Then we can showing the some water depth difference between the one cell. But HEC HMS, we just using one value per cell. That's the one limitation with HEC HMS. Okay, and then we also same 7 transfer function option in HEC HMS 2D. It's like a regular our lumped 2D sediment model. We have 7 option. We using same 7 option. That we provide the 4 grain size option: clay, silt, sand, gravel. But at this moment, we don't provide the AGU 21 option in here. Okay, for bed sorting and layer algorithm, we're using constant bed porosity to convert to the from the mass to the volume. And if we using some variable bed porosity, then we need more iteration. Then we need more kind of runtime. That's why we're using constant bed porosity. And then hiding exposure correction, that is a kind of armoring effect. We're trying to give some armoring effect, then that's why we put this kind of hiding and exposure correction. But at this moment, we just hard code it, not it's the option for user. Okay, and then finally we implement the finite volume method for 2D HEC HMS sediment transport. Okay, this is a kind of validation and verification with the published data. Okay, the first one is Leo data set. That is came from the Flume data set. You can see flow and some cumulative sediment load is pretty close with measured data. And the second set of data, Barfield data, is came from the agricultural small study plot. So you can see that some comparison with measured data as trend is pretty close with measured data. Last one is USDA Walnut Gulch experiment watershed data set. So also you can see flow and cumulative sediment is a pretty good match with measured data. With that, we need to ask, why do we need a 2D sediment transport method in HEC HMS? Okay, let me talk the advantage first. What is the advantage with the 2D? Okay, I bring some previous my study that is came from our lumped sediment model result. You can see each sub-basin, we can provide the sediment load and then some kind of information about the gradation, meaning is a percentage of each grain size. But we cannot provide inside this sub-basin. But some case, some project purpose, you need some information even inside this sub-basin, then you need a 2D sediment model. Okay, for example, this one is kind of result from the 2D sediment with 150 by 150 grid size. This one is cumulative sediment load. Blue color is erosion area, is red color is the deposition area. With this, you can see where is the deposit area, where is the erosion area. With that information, we can provide some information for kind of detailed TMDL study or BMP study. And especially for your sediment detention basin or catchment basin design, where is the best location? And then what is something, capacity for that basin? That kind of information we can provide with this 2D simulation. Okay. Another benefit, we can utilize remote sensing data like a LiDAR data, area photo data for validation or verification of for 2D sediment. Okay. Now I want to talk about the disadvantage. Disadvantage is time. Run time is so long. Is especially some sediment model. It's not like a flow model. It's kind of usually need some long-term simulation to get some annual average sediment load from this watershed. The mean is it's take some time. For example, this case is with this small watershed just only 3.3 square mile. With 150 by 150 grid size, 2-year simulation, 1 minute time step, with one core option with my laptop CPU speed 2.4, 16.5 hours just for one run. That's the huge run time. But we need to think about some solution. What is the solution with that? But sometimes, depend on your project purpose, you don't need this kind of fine grid size. You can kind of select proper grid size and time step, by minimizing your precision loss. For example, just one case, I'm just using same sub-watershed, but this time 1,000 by 1,000 grid size, 2-year, 15-minute time step this time, 8 core, 18-minute, 5-minute only. A huge difference, but you have a different resolution in terms of your result. Okay, I want to bring my case study. Okay, this case study located in the central Texas. We call Upper North Bosque River watershed. This area about the annual precipitation 750 and the soil type fine sandy loam. Okay, this one is my published something the paper result with HEC HMS rumped sediment model. As you can see here, we can provide pretty detailed sediment yield from each sub-basin with a different rate, and then we can provide some information for gradation information at the outlet. Also, we can provide the sediment deposition erosion through the channel area. But sometimes it's not enough. I want to see some more detailed information one sub-basin. That's why I pick up some SF20 this time. This area is a small 3.3 scale mile. Elevation difference about 170 feet. I used the 10-meter DEM for this time, and then whole grid size 4035 with 150 by 150 degree size. And this is one of output. This is accumulate bed change, but we can provide water depth, flow velocity, and then sediment concentration also too. Okay, let's move a little bit more detail. This is flow, okay, for 2.5-day simulation. First time I got one calibrated flow model. That is case 1, okay, 150 by 150 grid size. I got the calibrate model, but I want to check some different size of a grid because maybe I need some long-term simulation. But then I need to check kind of how much accuracy decreased with the different size of a grid. And then I made a different case. Case 2 is 300 by 300. Case 3 is 450, 600, 1,000 by 1,000. Case 5, that is all of them is 1 minute time step. And then I make a case 6, 1,000 by 1,000 grid size and the 15-minute time step. Okay, and then this is 2.5 day. You can see some runtime here. That is including flow and sediment. Case 1 is with 150 by 150, 3 minutes. But case 6, just 2 seconds. That's a huge difference. And then in terms of a flow calibration, if you change grid size and there's sometimes step, you need to recalibrate it. Okay, so this time I just concentrated 2 factors to calibrate for each different case. First one is M value, roughness factor. Second is constant loss rate. Using these 2 value, I can recalibrate it for each different case. For example, for M value, roughness factor, at this moment we don't have any kind of user interface to change this roughness factor from the HEC HMS. So right now I can change this value. We can find HDF file, output file. That is one of 2D output file from the HEC HMS. You just open this one. You can find the phase and elevation value, and then provide this kind of gridded value. Fourth column, this is M value, roughness factor for each grid. I just copy this one, paste it to my separate Excel spreadsheet. I changing that by ratio, and then paste again, and then close this file, and then run again. That's the kind of easiest way at this moment to calibrate HEC HMS sediment with this M value, different M value. Second factor, constant rate. This is easy. You just go to sub-basin level and loss tab, and then you put changes your constant loss rate. With changing that, I calibrate it. This value peak discharge is a measured one, about the 769, and peak time is 11. But this is each case calibrate value. It's pretty close. And then overall, we can check where the net subscript, the efficiency rate that came from our result tab. result summary table. So you can see it's all of them is about more than 90%. So either one fine if you choose any kind of different size of grid. But depend on your purpose. Maybe you need a more kind of a fine resolution. Maybe sometime then you need to go to more smaller one. This is a flow. This is a hydrograph comparison. It's a black dot here, solid line with black color. This is a measured one. And then red color is case one with 150 by 150. Green color solid line, that is case six. You can see the case one is kind of a match with the kind of peak timing. And then the both case six, case one is a peak rate is pretty close. But it's a kind of a lower, the peak is maybe different. This is black. Case one underestimated, case six overestimated. Kind of second one falling limb is both overestimated, but it's pretty much good. Now let me show you some special, result here. With the 150 by 150 grid size, this is hydraulic depth. If I check the one grid at the top upstream, then you can see time series water depth here. And then this is a downstream at the outlet. It's kind of 1.6 feet in a hydraulic water depth. And then for 1,000 by 1,000, it's a little bit bigger size. Then you can find that hydraulic depth upstream and downstream here. Now I want to move to sediment calibration. If you change grid size or time step, you need to calibrate flow. Then you need to calibrate sediment also too. Okay, so this is a different size. For sediment, I need to calibrate the two portion. One portion for chlorine parthenate parameter. That is for you, especially for a cohesive material for clay and silt. I need to change that. You can easily change this one from our user interface. You need to go to basin level, basin model level, and then sediment tab. As the first form number is for chlorine parthenate number. Also, you can change this kind of transport potential method here, but I don't want to recommend that the transport potential method changing after your first calibration just to change the grid size. You want to keep the same method. And the second one is 2D sediment erosion parameter. Okay, at this time, I just keep the same all of them. I just change the sediment total roughness factor for this different case with a different size of a grid. Okay, that one is you can change easily from the go to sub-basin level and then select erosion tab. You can change this value for your calibration. Okay, this is a kind of SETI graph. I just using 1 day cumulative sediment yield. This is a 1 day amount from the measured data. And then the black line is measured one. Same thing is a red line for in a case one. Green line is a case six. You can see difference between the measured data, but still pretty close. Okay, this is sediment. This one is a sediment to the special result. Same thing. I just click the same location from the upstream. This is pretty good. Through the time, you can see how much erosion from this cell and up to 0.03 feet through this 2.5 day. If I choose the sum about the outlet, then you can see this is a kind of deposit area through the time about 2 feet deposition. It's a great information for this kind of 2D sediment. And then move it to 1,000 by 1,000. Upstream is a little bit bigger size, is we have this much erosion, and then downstream we have this much deposition, but this time is 0.1, close to 0.1 feet, because it's average through the whole big size. But this time, 150 by 150, it's kind of pretty much channel area. That's why we have a 2 feet deposit. Okay. And then this one is animation result. The first one is left-hand side. This is sediment concentration through the time. You can see some concentration difference through the time. And the dark color is a high concentration. Light color is low concentration. Right-hand side is cumulated sediment yield through the time. As you can see, some erosion and deposition through the time. That is animation result. Okay. And then this one is a kind of a summary information based on my case study. Through the case study and then comparison with the published data, HEC HMS 2D flow and sediment result is pretty good match with the measured data. I can say like that. And then grid size, that's the big issue. But at least the user can optimize it or maximize their grid size, to the user's optimal resolution. So still we have a choice to reduce the some running time. Okay, final one. 2D model provide very useful information, especially for localized sediment issue. Okay, one for is kind of sediment reduction goal, like the TMDL study or the BMP study. It'll be good information. And then again, kind of a sediment-based location and capacity. That gonna be great information from the 2D sediment model. Okay. So this is my upper North Bosque River watershed sediment model. Okay, I have so many different basin model with a different case with a different size. But let me click the some 150 case 1. Okay, if you click that something in a basin model level sediment tab, that is a choice for your transport potential and then cohesive material, clone and parthenate. And then you have 4 input parameter for your clone and parthenate. You can calibrate this value for your clay and silt material. Then go to basin tab. Okay, you can go to here and then another erosion tab. You can change this to the sediment transport input parameter for your calibration. That's the major input for 2D sediment. And then compute option. Let me go back to 150 case 1. So one thing in here, special result. So for your during your just calibration, that you don't want to put the yes, because mean and no mean is it's not going to be generate your animation result. The mean is a less running time. But after calibration, you want to see some animation result. You want to put some yes, and then put your kind of a special or interval, output interval. For long-term simulation, maybe you can put the 1 day interval, maybe short-term, maybe less than 10 minutes or 5 minutes, something like that. Okay, that's the option. With that option, if you run that, and then you can go to result tab, and then you can see this is subbasin 1 and then 2D connection and sediment tab here. So you can see this is a concentration through the time, and then sediment total load, and then each grain size load here. Okay, and then for your animation, you need to put you run to the 150 case 1 here, and then change your information is bad change through the time. Then you can see this bad change simulation like that. Also, you can see each grain bad change rate, and then you can see each grain sediment concentration animation also too. I think this is my kind of last information. So thank you for your attention. Let me transfer to the Nick.
Thank you, Jay. All right, Nick, you want to go ahead and grab control real quick?
Yep. Hi, everyone. My name is Nick, and now I will do a quick demo of Redwood Creek project running on macOS with spatial results. So this is what it looks like for cell velocity spatial results on macOS.
So just to preface this for everybody, the reason that we're showing you this is because this has never been done before. The 2D flow and sediment transport capabilities have never been released for platforms other than Windows. So for those Mac users and those Linux users out there, you can use these capabilities in HMS. And that's a non-trivial amount of users too. We keep track of the people that are downloading from multiple platforms, and it's usually about 5 or 10% of the total downloads. So for a given year where we have 50,000 or 60,000 downloads, there's 5,000 or 6,000 non-Windows users out there. And we'd love to bring these capabilities to everybody and let them utilize them.
Yep.
So thank you, Nick, for that.
Thank you.
For sure. All right, so what types of studies are going to benefit from this type, from these enhancements? I'm specifically looking at things that have already been created, right? Models that already stand, have been created, they're working already, but you may want to add a little bit of detail to it. For instance, the SWIM's National Implementation Plan has generated over 150 HEC HMS models and counting for the continental United States. So they've used for forecasting capabilities, but you also use them for planning studies, right? Or dam safety studies, where project alternatives are being compared, or you want to sharpen the pencil, so to say. If you need more definition in a particular area to predict these effects, you can use these 2D capabilities without having to change anything else. So 99% of your model is unchanged. 99% of it is still going to be fine to use without any modifications. You want to change that one little area there? Go ahead and do that. You may need to change things downstream for sure if you're changing the way in which water leaves the 2D area and then goes through a whole bunch of other hydrologic routing reaches, but you can leave everything else unchanged and it'll still work. So other examples and types of studies that are going to benefit from this work include areas where, say, substantial physical changes have occurred, either due to wildfires or land use changes. So I just have a picture here of Detroit Dam from the Holiday Farm Fire. And that, or I don't know if that was a Holiday Farm Fire. I was working on a bunch of different fires in the Willamette River watershed. This is pretty drastic here. That has also happened for the Upper Snake. So to get at your question earlier, John, I know that there's been some fires within the Upper Snake River watershed, or the Big Lost River or Little Lost River, some of those additional tributaries in the area. If you're looking at significant changes where, man, I really got to know, I have no idea how hydrograph parameters are going to change given this burned area, a whole bunch of downed trees, vegetation on the ground, or sediment transport. Look at all that loose duff that's now there that's been burned and it's going to be easily mobilized. You can use these capabilities to better hone in on anticipated changes given that area. Same thing for other land use changes. You can also look at this for reservoir sedimentation studies, right? I want to know how much sediment is coming into Detroit lake. So what would I do in this case? These capabilities can help you there. And non-point source sediment studies. So if you have a whole bunch of different areas where these things can be coming from, it's not a single location, hopefully they'll help you in this case. I want to hit it tech transfer real quick. So we initially released these features, if you're paying attention, in version 4.7. The last official release that we have on our website right now is version 4.8, but we're hoping to release version 4.9 very soon. Every single release, we're making benefits. So as the solver is made better, improved, we release that within HMS as well. So in between version 4.7 and 4.8, there was essentially a 100% increase in compute speed. And we've even made increased performance for sediment transport recently as well. So you get all of that with these new releases as well, and making bug fixes along the way and enhancements along the way. On the left, I got a link there to our website where you can go and grab the latest download, check out the latest beta for version 4.9 as well. We've also included a whole bunch of documentation. So beyond just the user's manual of how you access these features in the user interface, turn things on, change parameters, whatever, we have a whole bunch of tutorials and guides that go along with that. I included a specific one in the chat earlier on how you can use these features to parameterize variable Clark parameters, so your times to concentration and watershed storage coefficients. But you can also use this for other capabilities, right? So I have a simple and a complex example that's included in there as well. Plus, we also have a tutorial that has to deal with base flow and interflow choices when using these capabilities as well. So definitely go and check those out. All right, now to next steps. The USACE R&D program paid for this development and implementation. So thank you. I want to say thank you again to everybody that's involved with that. Made that happen in the past. We wouldn't be here without that. We wouldn't be talking about these features without that program. So thank you. But this isn't the end, right? We've already highlighted a few things that we want to make better in the future. So we have a huge list of things here, a never-ending list of stuff that we want to work on here, and additional topics that we really want to investigate. Some of the major things: what to do with post-fire, right? How does fire change the way water moves on the overland surface? How does water change, or how does fire change the way that water infiltrates and exfiltrates again? How does it change sediment transport? Things like that. We really have a lot of work to do ahead of us and a lot of interesting research that's ongoing. If you're interested in any of that, please reach out. I'll do my best to connect you as much as possible. Customers within USACE and outside USACE have also seen these features, and they're providing funding to continue development and integration of new stuff. Some of the things that are shown here are specifically related to those requests from others. So if you have requests, if you wanted to see it do new and unique things, hit us up. Let's talk about it. We'll see what we can do to partner. All right, just in conclusion, I want to leave some time here to go over some questions. Just to make everybody aware, 2D flow and sediment capabilities are up and running in HEC HMS. So they've been out and about since version 4.7, since last November, I think it was. But we have an upcoming release, version 4.9, that I'd really like to get everybody's opinion on. If you haven't grabbed it already, please go grab that beta from our website. Give it a shot. Let me know how it goes for you. Got a whole bunch of interested partners, both within the Army Corps of Engineers and outside, the federal government and on down, that are currently using these enhancements. And they're investing in additional enhancements. So I'm really, really pumped up to see that. I want to know how they work for you, what works and what doesn't work. So definitely feel free to reach out. All right, let's go through some of the cool questions that we got in here. Matt, you want to help me out with some of these? I know I identified a few. I'll start with that.
I'll start from the top, the first one there. So what is the purpose of adaptive time step? And is it to increase speed, provide shorter run times? And then notice that RAS models with adaptive time steps tend to be less stable.
They can be, not always. The reason we turn this on is because it's been shown to work pretty well for us in our testing. We haven't applied it to every single modeling domain that's out there, but adaptive time step does work pretty well. When it doesn't work well, just turn it over to the fixed time step. I've definitely seen cases where adaptive time step can lead to some troubles, either instabilities or longer run times, but their intent is to increase stability and make the simulation actually produce more accurate results.
All right, let's jump to your favorite model, the upper snake.
Yeah, for sure. So like I said earlier, there's been a lot of ongoing change within the Upper Snake River watershed. And there's also some other applications too. For instance, I know that there's been a lot of interest downstream of, say, Ryrie Dam and the communities that live there. A lot of other locations, the channels just kind of disappear, right? You just have release from a reservoir into a channel that used to go the whole way to the Snake River, but it kind of doesn't anymore. It's all pumped out and used for irrigation and whatnot. But when it rains really hard, you have a bunch of snowmelt, that water is going to go somewhere. So in particular, I forget what the name of it was, Gordon Dam? I forget what the name of it was. I'm sure John is screaming it into his microphone right now. When you got water that just kind of like goes on the overland plane, is going to go wherever, these 2D flow capabilities can help you there as well. So where you want detail, where you need detail, these will help you out.
Yep. Let's jump to Jay here. I got a question for you, Jay. So for HMS, either lumped or basin average or the 2D sediment that you talked about, have you developed models for sediment erosion for like seasonal or annual type of sediment loads? Could HMS be used for annual sediment loads?
Yes, kind of. With this long-term simulation result, we can generate some annual sediment load. So that's the possible. I think I tested with the lumped model with the previous HEC HMS lumped sediment model. And then I'm using this 2D sediment simulate up to 2 years. So it will take us some time, but we can generate the annual average sediment load from the watershed with this 2D and lumped model. Yes, I can say yes.
Jay, do you mind just in the chat box here in just a second, drop in a link to your paper for the Upper North Bosque? So you at least have an example there with lumped or subbasin average and running this continuous simulation.
Sure. I think that I cannot provide that link because that is limited for kind of from the AWRA the publication something limitation. But I can send that one my kind of hard copy PDF file. So.
All right. Let's see
So
here.
Russ also asked about a threshold for shallow slopes. So that depends upon the routines. Kinematic wave starts to break down for anything less than, say, 10 feet per mile. The neglected terms in the momentum equation start to fail. But I don't think too many people are using kinematic wave for major channels that aren't super duper steep. The other threshold to take into consideration is approximately 2 feet per mile. So even Muskingum Cunge starts to fail when you start to get around there because the neglected terms in the momentum equation start to matter more and more and more. Diffusion wave does a better job when slopes get shallower and shallower, but even they have a breaking point, a tipping point. The only way that you can, the best recreation of all those features are using the full momentum equations, which aren't currently available in HMS, but we do have plans of opening that up and allowing access to those through the solver. So keep in mind, approximately 2 feet per mile, most things start to fail. 10 feet per mile, kinematic wave starts to fail there.
All right, looks like we have a question here that hasn't been answered yet. Can you use HMS to develop the time area diagrams using the newer GIS tools? I know we've been talking about it. Any idea, Mike, when that might happen?
You can. I've been interested in doing that for a while, and I've had others reach out to see about that as well. That's essentially what ModClark does, right? You don't have to use the default time area histogram that's inherent within the Clark unihydrograph method, which assumes that your watershed is an elliptical shape. ModClark gives it a sub-basin specific time area histogram. You can use 2D Flow for that to develop your time area histograms, but check out the link that I threw in there earlier. Matt had a really, really great tutorial and guide on how to develop the variable Clark methods. So that allows time of concentration in R to change throughout a simulation based upon the excess precipitation rate. That's another place where these capabilities really come in handy. When you start to extrapolate with unihydrograph theory, say you calibrate it to events that had excess precipitation rates of ½ an inch or 1 inch per hour, and then you go to simulate, say, the PMP or the PMF, where you have 8 inches per hour of excess precipitation. That's so far beyond anything that you've used to calibrate your TC&R parameters that unihydrograph theory starts to flop. That's why we've always included either the 25 or 50% peaking rates in most PMF studies in the Corps of Engineers. So over the past 5, 6, 7 years, we've really started to get at, well, let's, instead of doing that kind of back of the envelope change, let's actually make those simulations. Let's do this like quantitatively. So 2D Flow helps you do that. You don't need to use unihydrograph theory and that limitation, but you can use 2D Flow to help you parameterize variable Clark parameters that change throughout your simulation as well. And Matt has a great tutorial and guide that shows that there. And I know there's been other applications to do that as well. I know Landon, he specifically did one in the Texas area. They've been done from time to time. Very cool to read those. Any other questions?
I think you've addressed all the ones in the chat box.
Nice, and right on time too. If we didn't get any questions or you didn't add your question in here, please hit us up, send us an email. And especially if you're using these features, I want to know how everything is going. I want to thank you guys for attending and paying attention, asking great questions. Really appreciate it. Jay, any closing comments from you?
Oh, thank you for attention.
Yeah, much appreciated. Thanks, everybody. We'll post this video to our website soon. We'll send out a list to everybody that's on the email list. If you haven't been on the email list, check out the link that Tommy put in the chat here, or check out our website to get on there, and we'll send everybody a link to the presentation when it's ready. Thank you. Everybody have a good one. Stay safe.
Thank you.